This is the program we use. The program reserves buffer size of 500 bytes. This buffer is declared in the stack. We put in a very long string so it overflows the stack and tampers the return address. In this return address, we place the address to the malicious piece of shellcode. Ginop is a GDB peda command. Here we created a string of size 512 bytes. We input it into the program, but this does not cause any segmentation fault issue because 512 byte is reserved in the memory. 512 plus 8 is 520 byte. 8 byte is the base pointer size. So if we use 520 bytes, it causes a segmentation fault. By inserting one more byte into the input string, we can see that the return address getting replaced with new byte, that is A. We then replace the other 6 bytes with A. Why 6 bytes? Because the canonical or the usable address space is only 48 bits long. Here we overwrite the return address with AAAA. AA corresponds to 41 hex. /x90 is the NOP operation in Intel microprocessor. We are going to create a NOP slet. We have previously seen that how this address was replaced with 414141. Later in this tutorial, we will replace it with the address that points to the NOP slet. Here goes our malicious piece of code, which will be explained later. This command is used to display the memory addresses and the contents in them. This is our NOP-slet and the payload. All the characters after the last /x90 is our payload. This long string forms the blue and red part of this figure, that is the NOP-slet and the payload. Here we are trying to find the number of NOP instructions needed. 526 bytes input will override the instruction pointer. 27 bytes is the size of the payload. 60 is actually 6 into 10, where 6 bytes is the size of address that points to a point in the NOP slet. This address is pasted 10 times into the stack, and finally, that is the 10th time, it overwrites the instruction pointer. 10 is better than 1 because we have a better chance of bypassing OS security strategy to prevent buffer overflow. Here we are actually finding the address to the knob slit. Since Intel processor follows little endian, we insert the address in the reverse order. This address is of 6 bytes, uh, 6 into 10, as mentioned before in this tutorial. We are feeding it as an input to our program bof.c. So the instruction pointer points to the knob slit, and from there it moves on to the malicious code. We have now successfully entered into a terminal where various commands works.